Hey everyone, welcome back from break. We are this week looking at something called one-dimensional motion. And the nice thing is the math here is no different from what we've been doing. So it's a good place to come back and remember how to find first derivatives, second derivatives, find where the function's increasing, decreasing, find concavity. We're going to be doing all that again. But literally, we're just going to turn it into more of a physics-based view as opposed to just graphical and concavity view. But we keep it very simple. So if you're in physics and that scares you a little bit, don't worry. This is a watered down physics. But the reason this is an important topic going forward is if you were to go into more advanced physics, you would just expand these ideas. So yeah, this is pretty basic. It's one-dimensional motion, which I'll go into in a second. But once you go up into higher levels of math, calculus, and then you go into engineering courses, you can extrapolate all this to multivariable calculus and things where you have a lot more going on. So we're basically just going to be looking at a function with one variable, and it's going to be a position function. So let me explain. Let's say we have a position function of a particle. Typically, they use the phrase particle in this course because a particle just implies we're not worried about friction or mass or any of those other things in physics that would cause it to be a much more difficult problem. So we're eliminating all the other variables. We're focusing on just two variables, time and position. So I give you this function, and time is in t, so t is time, and we'll say that that's in seconds. Typically it's seconds, and then we'll say p of t, the position, is in meters. Okay, so here's the idea. You have a particle, and say it's right here. Particle moves in one dimension, which means either it moves forwards and backwards, that's it. It can move left on yours and right, left and right. Or in the problem, it could say a particle is moving up and down. So a lot of times we do left and right or forward, backwards. Sometimes we do up and down. It just means it's moving in one direction and then or the reverse direction. That's it. It's not moving all over the place. So a particle is moving left, and then right. It's a mirror for me. But one-dimensional motion, okay? That's what's going on here. So if I give you this position function, I can tell where the particle is at any time I want. So for example, where is the particle at t equals 0? Well, that's as simple as literally plugging in 0 to the function, and we can figure out where its location is, 6 meters. It's at the 6 meter point. What on earth does that mean? Let's say that this particle was traveling left and right. So here's the path the particle could be taking. Not straight, but whatever. Let's say that this is the 0 position. Right now, 1, 2, 3, 4, 5, 6, at time 0, your particle is right there on that line. That's where it's starting. So if I have kind of a street or something and I've marked a position as being at position 0, your particle is starting out at position 6 at time 0. By the way, when I ask you where I'm at time 0, this is sometimes known as an initial condition. It's where I'm starting out. Okay, if I want to know where I was at time 1, so let's say I asked you what time or where am I at, what position am I at time 1? Well, that'd be as simple as plugging 1 into the function. You get 1 minus 5 plus 3 plus 6 equals, that looks like 9, 10 minus 5 is 5, right? Oh, so what happened? In the 1 second, it looks like it went this direction. I guess I should do it this way. It went, and now here, at t equals 1, it's at position 5. It went left or backwards. Interesting. So think about it as this little particle. It's just moving around left and right. It's going left, it's going right, it's going, that's it. At different times, it's at different positions. So a lot of the analysis we'll be doing is me asking you questions like, when did the particle stop? When did the particle change directions? When was the particle moving forwards? When was the particle moving backwards? When was the particle speeding up? When was the particle slowing down? Those are your typical questions I will be asking you. So let's go into how to do some of this. Well, I start you with the position function. Everything we're about to do, you have done before. when we have found the first derivative test and we've used the second derivative to determine concavity, we're going to do all that again. So here's what you're going to do. When you encounter a motion problem like this, so this is called motion problems, one-dimensional motion, where I give you a position function, you should begin by finding the derivative right off the bat. Why? Because that will give you the rate of change of position. And if you're in physics, you know that that's something called velocity. So this will give you velocity. Velocity. So velocity is kind of like speed, a little bit. We'll get more into that in a second. So take the derivative, you get 3t squared minus 10t plus 3. That factors. So in other words, you should be doing like we've done, to find critical points. So 3t minus. Okay, so it looks like we have two critical points. T equals 1/3, t equals 3. Okay, did I do that right? I hope I did. Looks like I did. Two critical points, put them on your first derivative number line and label it. This time we're talking about velocity, so we'll label it like that. Plug in a very positive number like 50, you get positive, increasing. Plug in 2, you get negative, decreasing. Plug in 0, works, you get positive. Okay. One more thing, when we're dealing with motion, typically time starts at 0. So t equals 0 is when you can start your number line. We don't really deal with negative time too much. We usually have time start at 0. All right, let's continue along. Find this derivative of velocity. Well, what on earth does the derivative of velocity mean? We've already been talking about it a little bit, but now if you think about what happens if my speed speeds up, my rate of change has a rate of change, that's known as your acceleration. So that's called acceleration. So we can take the derivative of the derivative to get acceleration, 6t minus 10. And that gives you an inflection point. T equals 10/6 or 5/3. Put that on a number line. It's right there. This is our acceleration number line. Positive, which means concave up. Negative, which means concave down. Okay, so we've done all this math, but I haven't even asked you a question yet. But that's a good thing, because now I can start to ask you really interesting questions. So for example, some of the things I'm going to ask you would be like this. Let's do this. When is the particle at rest? When did it stop? So the particle's doing this. It's going forwards or to the right. It's stopping and then it's changing direction, going backwards. It actually stops one more time and then goes forward again. How do you know when it's doing that? Well, that deals entirely with the velocity. It's when the velocity is 0. If my velocity is 0, it means I'm not moving. So my velocity is 0. That's when the particle is at rest. And you already found that. Oh my gosh, it's the critical points. So at t equals 1/3, this particle stopped for a second. And at t equals 3, this particle stopped for a second. It's the critical points. So the critical points are where your particle stops. So if I have a position function where the derivative is 0, that means the particle is not moving. It stopped for an instant. It actually changed directions. So let's get to the next important question. When is the particle moving forward? When is the particle moving forward? Well, literally, when is it moving forward? That's exactly the same as when it has positive velocity, or when the position function is increasing, right? Because if my position is increasing, it means I am moving forward or to the right or up. So remember, it depends on which plane we're talking about. But if I say forward or right or up, it's all the same question. And you've already done that. Look, right here. In this interval and this interval. So we would say from 0 to 1/3. I put a bracket because at time 0, we're actually already moving. We have an initial velocity. If you plugged in 0 to the velocity function, you'd get 3. We'll do that in a second. And then from 3 to infinity whenever we're stopping our time interval. So this particle basically moved forward for 1/3 of a second. Oh no, My thing froze. Sorry, one sec. Moved forward for a third of a second. Uh-oh. Please tell me this didn't freeze. It looks like it's still working. Okay. Moved forward for a third of a second. Stopped. Moved backwards from 1/3 second to the 3-second mark. And then at the 3-second mark, we moved forward again. Okay. So that's what's going on in terms of when the particle is moving forward. So when was it moving backward? Backwards, which means left or down, depending on which plane we're talking about. That would be from 1/3 to 3. So the velocity is telling you about when we are moving forwards or backwards, left or right, up or down. And then other questions I could ask you would be like, what's the velocity at time 0? So like, for example, what's the velocity at t equals 0? Plug 0 into the velocity function. So we have my velocity function over there. V of 0 is 3. Now we're going to start getting into units a little bit. What are the units on velocity? It's not meters. If you're in physics, you probably know it's meters per second. Meters per second. It's how many meters you're changing as every second is changing. So it's kind of like your dy dx. The change in y, which is meters, the change in x, which is seconds. So meters per second. At that instant, we are traveling 3 meters per second, which means we are traveling forwards. Okay? So at the 0-second mark, we were traveling forwards. 1/3 second, we traveled backwards though. So we traveled forward for like an instant. Well, a few instants, and then we traveled backwards. Okay, let me ask you another question. Zoom out a little bit. What if I asked you a question like this? What is my speed, or the particle speed, at t equals 2? Well, speed and velocity are related, so let's plug 2 into the velocity, because that's how we're going to have to do it to find the part of the answer. Oops. So we're going to plug 2 into the velocity function. And this is going to be important for next lesson, but it's a little preview. 2 squared is 4, 12 minus 20 is -8, plus 3 is -5. Good. We're moving backwards. That's what velocity means. So the velocity at time 2 is -5 meters per second. However, speed, and here's the important part, speed is always positive. When you're telling someone how fast you traveled today, like how fast are you going? You don't say, oh, -3 or -10 miles per hour. Like you don't say that, because when we're talking about speed, we don't talk about direction. If you have a negative velocity, you're going backwards, positive velocity forwards, but speed is always the absolute value of velocity, which is just then it would be 5. So in this case, you'd say, oh, at the time 2, I was going 5 meters per second backwards. At time 2, I was going 5 meters per second backwards. So speed will come into play a little bit more when we get to the next lesson, not today, about when we're speeding up and slowing down. Because think about it, if this particle is moving all over the place, it slows down, comes to a stop, then speeds up, and then slows down and comes to a stop, and then speeds up. So there's going to be a little bit more we add to this. And then finally, other questions I can ask you. Like I could ask you, and we'll get more into this again next lesson. The acceleration comes more into play next time. What is the acceleration at t equals, I don't know, 4? Well, that's as simple as plugging 4 into the acceleration function, and you get 24 minus 10 is 14. Now, what are the units on acceleration? It's meters per second. Meters per second. That's how we measure acceleration. It's the position over the rate of change of the x variable, which in this case is time. Typically, you don't write meters per second though. You would write it as 14 meters per second squared. Meters per second squared. We don't get a lot into it. Basically, what you need to know is when we're talking about velocity, it's units per time, so meters per second. When we're talking about acceleration, it's units per time squared, or meters per second squared. That's about it. We're not going to go too much into all of the dimensional analysis in this course. That'll play a bigger role second semester, but again, not in terms of having to find it yourself, more just remembering that velocity is units per second, acceleration is units per second squared. Okay, so this is pretty much what you're going to be doing today. I will give you a position function. Sometimes it's p of t, sometimes it's x of t. You're going to go through and do all of the first derivative, second derivative, number line stuff, just like before, but now you're changing it into language of physics as opposed to language of calculus with concavity and stuff. Okay, the last thing. Here is the graph of the position. So I'm actually going to do this. I ask you to do this on the discussion. I want to know what's going on. How can you look at this position function and tell me what's going on in terms of motion? Well, remember, this down here is your time axis. This is your position axis. So what is this particle's position? And that's, remember, we already found that at time 0. So this is time 0. We started out at position 6. People always get confused because they think that this right here is this down here is the path the particle's taking. It's not. This is, remember, it's one-dimensional. It's just giving you the position at each time. So like, for example, at time 1, I am right here, position 5. So what's the particle doing? It moved forward. So I'm going to trace along and explain to you what's happening as we go. Ready? Let's change my color. Mr. Particle is moving forward, stops, starts moving backward, starts moving back, more backward, moves more backward, slows down, stops. Mr. Particle moves forward, and just continues moving forward and speeding up till the end of time. Okay, so Mr. Particle stopped here. Mr. Particle stopped here. Okay, so ready? You're going to watch me do this because remember, it's one-dimensional. So I'm going to do it right over here on the x-axis right here, or right underneath the graph. So if the particle is moving along the x-axis and it's starting right here, ready? It did this. It started at position 6. So let's just pretend like we have this little particle. It moved backwards, it moved forward for a little bit. At time 1/3, it started moving backwards, until time, and then it actually went all the way to, it looks like -3. And then at time 3, it started going forward again, and it moved forward for the rest of time. Okay, do you see what I'm saying? This graph is a time position graph. It's showing you the position at each time this particle is located. All this particle is doing is sitting on a line and either moving forwards or backwards. Okay, one more time. I guess you can always go back and rewatch it, but one more time, I'll explain it to you. Let's do a different color. So Mr. Particle started right here, moved forward for a tiny bit, didn't quite get up to that far, but then bam, started going backwards. Oh, geez. Sorry, my hand slipped. Well, kept going backwards until it hit, looks like it ends at position -3, but then at time 3, it started moving forward again. Okay, that's what the particle is doing. So it's kind of doing this type of thing. But imagine that's all on top of itself. That's how you look at the change of position as time is going by. And not only that, I can figure out how fast it's going at different times and all these important characteristics of acceleration and speeding up and slowing down, which we'll get to next time. Okay, and in second semester, we really do crazy stuff with this. But this is the beginnings of particular motion or one-dimensional motion. All right, we'll stop there. Just one example, but it's all, again, literally the same stuff we've been doing with derivatives and second derivatives. So hopefully you remember how to find those. All right.